Hello, welcome to this module. In the previous module what we have seen lithography technique, and in that I told you that let us see how the deposition of a film happens on the substrate before which we can perform the lithography. So, what does that mean? Let us say this is a substrate. On this substrate, let us say this is a substrate, let us say this is silicon substrate. Okay. So, it looks like this. Okay. Now, I want to deposit a film. So, it starts looking like this. After depositing a film, I have to pattern it, right. So, some of the area the film is protected, remaining area is etched. That patterning is called lithography, and if you use photons, photolithography. Now, the question is how can I deposit on this substrate this film, right. So, there are techniques which are called thin film deposition technique. A film which is thin, when you say thin, is a few microns, in fact less than a micron in most of the cases, and the deposition is done under vacuum, and that is why it is also called vacuum deposition technique. Now, we will see why it is called vacuum deposition and what is the role of the vacuum in depositing these films in a while. For you to understand the concept, if you see the slide, let me just show you the concept. So, the topic is thin film deposition technique techniques. If you take a substrate, okay, and let us say that I have a glass substrate, glass, on which I want to pattern aluminum electrodes, all right. So, the top view would look like this, okay, or you can say like this, but the cross sectional view will look like this. Now, the point is how can I pattern aluminum electrodes on this glass? First is that I have to deposit aluminum on this glass wafer, right, and then I can perform lithography where you have your photoresist. Let us say we draw photoresist like this, photoresist, then you have your mask. Of course, you have to perform soft bake, then mask will look like this, is a bright field mask, and once you load the mask, you have to align the mask with the wafer alignment step. Once you align the mask with the wafer, what happens? You can make a hard contact. After that, so this is our bright field mask, and then you can expose this wafer with UV light. After that, you have to unload the mask and develop the wafer. When you develop the wafer, what it will look like? You have a glass and you have a aluminum, and the photoresist would be in 4 different places, because the unexposed region will be stronger since our photoresist is positive photoresist. So, this is what we will get. After that, what is this one? This is our aluminum, right. So, after that, this is my photoresist, this is aluminum. If I dip this, or if I place this wafer in aluminum etchant, it is called aluminum etch, then what will happen? We will have, if I dip this wafer in aluminum etchant, what I will have? Let me just draw it here. I will say that this is the wafer that we are placing in AL etching. I will have my wafer which will look like this. Okay. What I have? I have, oh sorry, it is not correct. I will have my wafer like this, where your aluminum is at the bottom and the photoresist is at the top. what happens is the aluminum etchant will etch aluminum from the area which is not protected by photoresist. So, you have aluminum, you have positive photoresist and you have glass. Now, if I dip this wafer in acetone, before dipping in see the process would be you have aluminum which is this layer, then you have photoresist, you spin coat photoresist, soft bake, align, expose, develop. After developing you have to go for hard bake, after that you etch aluminum from the area which is not protected by photoresist and then dip the wafer in acetone. Always remember, after every chemical etching step you have to rinse the wafer with DI water, you have to rinse the wafer with DI water and then dry the wafer with nitrogen gas. Alright, this is a process by default. Always remember, any chemical when you use, you have to do this step. Okay. Now, if I dip the wafer in acetone, what will happen? Acetone is the stripper, it is stripper for your photoresist. So, acetone will get etched and you will have this particular wafer, or you can say glass substrate with aluminum interdigitated electrode patterned using photolithography technique. The question here is how we got aluminum layer deposited on the glass substrate, and the answer is PVD, which is called physical vapor deposition technique. Cool. So, physical vapor deposition technique is a more versatile method than CVD. What do you think by what do you mean by CVD? CVD is chemical vapor deposition technique. Now, why PVD is more versatile than CVD? Because PVD allows to deposit almost all materials used in fabrication. That means, it can allow us to deposit metals, it can allow us to deposit semiconductors, it allows us to deposit insulators, alright, metals, aluminum, gold, chrome, platinum, tungsten, zinc, tin. Tin is not T, okay. Tin is SN, alright. So, lot of metals we can deposit, semiconductor, silicon, germanium, we can deposit very easily, insulators, SiO2, Si3 and 4, silicon dioxide, silicon nitride, and so on and so forth. So, the in PVD the surface reaction occurs very rapidly, and so very little time for rearrangement of the atoms, and that is why the you will see that the orientation of the atoms is random in most of the cases when you take the PVD technique, while there is a effect of this on the thickness uniformity of the metal or a material that we deposit on the substrate. What does that mean? If you see the slide, that you can see that because of the higher or faster surface reaction or rapid surface reaction, the thickness uniformity, shadowing by surface topography and step coverage can be very important issues in physical vapor deposition. Alright. So, the uniformity, step coverage and the topography will get affected in PVD. However, there are ways to overcome these limitations, and let us see in this module thermal evaporation, e-beam evaporation and sputtering. So, when you always talk about physical vapor deposition, it is generally in 3 steps or 3 different processes. One is called evaporation, which is thermal evaporation. Then another one is called electron beam evaporation, and third one is called sputtering method to deposit the material onto the substrate. The first two are electrical, while sputtering is mechanical way of dislodging the atoms and depositing onto a substrate. We will look into that in detail in few slides. So, let us start with your physical vapor deposition, and as I told you, the physical vapor deposition mainly it is divided into two, where evaporation can be further divided in thermal and e-beam. Okay, thermal and e-beam. So, physical vapor methods produce the atoms that deposit on the substrate. Evaporation and sputtering are two different techniques. Sometimes this thermal evaporation or the physical vapor deposition is also called vacuum deposition technique, because the process is usually done in the evacuated chamber, that means chamber without air, that means chamber with vacuum. So, generally PVD is used for depositing metals, however dielectric material can also be deposited. Now, let me show you what are the photographs in this particular slide. The photograph on the bottom right is thermal evaporation system. It is a manual thermal evaporation system, that means we have to open the chamber, we have to load the material, and then we have to create a vacuum by using the electronics over here, and then you use the heating to evaporate the material. So, we will go in stepwise, do not worry about it, that what are the further steps. The point is there is a requirement of personnel next to the system to operate the system, manual way of thermal evaporating. The second image that I will show you, which is on the top right, which is this one, is your semi automated thermal evaporation system. Alright, this one, the bottom is manual thermal evaporation, the one on the top is semi automated thermal evaporation, and finally in this case this is electron beam evaporation. Okay. So, we have two thermal evaporation, let us say TE, one is the E beam evaporation, EBE. Okay. This is not a short form. So, in exam do not write TE and EB, okay. It is just like I am showing it to you, so that it is easy for you to understand, rather than writing the entire electron beam evaporation, I am just writing EBE. Okay. So, let us further understand the thermal evaporation technique in the next slide. So, evaporation techniques, particularly when you talk about PVD, a vacuum chamber is pumped down to less than 10 raised to power minus 5 torr, and evaporation of atoms from the surface or source condense on the surface of wafer. Now, what does that mean, right? So, let me just show it to you in one more slide, which is right over here, right. Let us delete these things. Yeah. So, what does that mean? That you have a chamber, okay, and then on the top there is a wafer holder, in the bottom there is a source holder. What is this called? Source holder. This is called wafer holder, alright, on which you can place wafer. This wafer is holded by some pins, okay, or there are slots, and this source holder, it is also called boat, alright. It can be boat, it can be coil. Now, I will explain it, do not worry about it. So, the source is placed inside the boat. What is this source? These are aluminum pellets. If you want to have semiconductor pellets, if you want to have insulator. So, the point is here we are talking about aluminum. So, aluminum pellets. Now, this boat is made up of a metal. The chamber is evacuated, that means there is a creation of vacuum, approximately 10 to the power minus 5, generally it is greater than 10 raised to minus 6, higher the vacuum better your quality of the film. Now, the system is called thermal evaporation system, thermal evaporation system. Why? Because you have to apply a voltage across this, funny no, our chamber, I can delete the chamber, so powerful. So, anyway, so the point is these are of course wafer 1, let us say 1, 2, 3, 4. I have to apply a voltage across my boat which is a metal, alright. What will happen? Voltage is there is a metal, that means there is a resistance. So, there will be flow of current. Now, metal has extremely low resistance and that is why the current flowing through the boat will be extremely high. So, there will be I square R heating, which is also called Joule's heating, and because of that the metal which is aluminum inside the boat will start melting, right. So, we will say boat metal as Bm. We can also say instead of boat source metal, right, because this is a source, right. So, source metal, source can be boat, source can be coil. Okay. So, source metal, and then we will say source metal temperature, and we will have the material that we want to deposit. So, let us say deposition metal temperature, in this case aluminum is there. So, we say deposition metal which is DMT, and source metal is SM and temperature is T. Always remember that the SMT should be greater than DMT. That means the melting point of SMT would be very high compared to the melting point of the deposition metal. That means of course, the source metal should be higher than deposition metal, then only deposition metal will get evaporated, but also important thing is the melting point of the source metal is also very high than melting point of the deposition material. Okay. So, if I apply voltage, there will be flow of current. Because of flow of current, the source metal will heat. When it heats, the material inside which is aluminum will also get heat and heated up, and it will melt. When it melts, it will start evaporating and condensing on the substrate, right. So, we are thermally evaporating a material which is holded on to the source, and that is why this technique is called thermal evaporation. Now, the question is why my melting point, or why the melting point of the source material should be extremely high than the deposition material. The answer is that if your source material is equal to melting point, what will happen, that the source will also start evaporating. We do not want source material to get evaporated, right. We want aluminum to get deposited. We do not want our source metal to also get deposited along with aluminum, otherwise it will become alloy. It is a two different materials, two different metals that will be evaporating. So, we require the source metal to be at extremely high temperature compared to the deposition material. Okay. Now, the another question that we should ask is what should be the vacuum in this evaporation system, and the answer is the vacuum should be extremely high, that means -6 or -7 torr. In fact, anything which is greater than 10 to -5 we can use in the system. So, the point is, what is the requirement of having a vacuum? Why we cannot deposit the material in the ambient situation, in the air, right. So, for that there is a reason, and let us see the reason in few slides to help you out. The technique or the process is called mean free path, or the parameter is called mean free path. And what does mean free path means? Mean free path means the average distance a molecule travels before it collides. That means, if I have this chamber, how much my this melted material would travel to my wafer before hitting an atom, because there will be some atoms, right. There is a vacuum, but still some atoms will be left. So, if I start evaporating, at some point of time, as you see this, there is a possibility of hitting with this, hitting with this, hitting with this, hitting with this, right. How much length it can travel before it hits the atom is called mean free path, and this mean free path can be increased by having a higher vacuum inside the chamber. So, that is what it is say, it is written here that average distance a molecule travels before it collides with another atom, and in other words, after melting how far the vapor travels in the chamber before it hits the residuous gas molecule. That means the gas molecule which are here, I said the atom, but that is not a correct way to express it. There will be gas molecules inside the chamber, and those gas molecules we evacuate it by using vacuum. However, the remaining gas molecules would be there inside the chamber. When the material deposits, it will hit those gas molecules. How long it can travel before hitting the gas molecules is our mean free path, and you can see from the equation here it is given by lambda equals to, if you see the slide, lambda equals to kT by under root of 2 pi p d square, where T is absolute temperature of the chamber, D is gas molecule diameter, P is pressure, and K is your Boltzmann constant. Now, let us see an example of a mean free path. So, if you consider a nitrogen gas molecule whose diameter of 3 angstrom and the temperature of the chamber is about 300 Kelvin, then if you want to calculate the mean free path, what should be the answer? The D is given by 3 angstrom and T is 300 Kelvin. Now, we already have equation lambda equals to kT by root 2 pi p d square. So, if we put these values in the equation, we will have P equals to 10 to the power minus 6 torr and lambda equals to 78 meter. That means the gas molecule can travel for 78 meter without any collision with the other molecule. If the pressure is minus 7, the 78 meter will become larger. If the pressure is minus 5, it will become smaller. So, what I told you that the source material, we can say it is a boat which is shown here, or it can be coils, this is a basket, right. So, it can be different materials in which we can load the source material or deposition material. So, we have tungsten wire sources. Tungsten is used as a crucible material, and this evaporant wets tungsten and retained by surface tension. The refractory metal sheet sources are tungsten, tantalum and molybdenum. And for sublimation furnaces we use sulfides, selenides and some oxides as pellets, while for crucible materials we use generally Al2O3 or BN or graphite and refractory metals, normally heated by external tungsten wire or heating elements, and sometimes a high frequency induction heater can be used for heating this particular source materials. So, let us understand the first topic of the PVD, and that is our thermal evaporation system. So, the thermal evaporation system, as you can see, there is a chamber and then there are wafers which are loaded on the wafer holder. There is a source in which you have loaded the material, and then when you heat this material it will. So, this is an actual schematic of within the chamber. There are 4 source holders 1, 2, 3 and 4, and if you see carefully you can load the boat between these two, this 2 and this 2. Okay. So, the point is a 4 source system, and you apply a voltage through this particular bar. This is 1, voltage 2, voltage 3 and voltage 4, and the board that is connected between these two electrode will get heated up when you apply a high voltage because of the low resistance of the board. So, surface reaction usually occurs very rapidly and there is very little rearrangement, as we have seen earlier. Thickness uniformity and shadowing by surface tomography and step coverage are some of the issues. Let me play 3 videos which are about the thermal evaporation system. This is a video 1. let us see how this occurs in the actual system. I will play this video as well.
एक राहू दे. हां कर बंद. हां.
So, what you see here is these are videos for thermal evaporation system. Now, if you see the system again, you see the slide, and let us finish this the module here, then I will come with the next one where there is a alloy and what kind of temperature can be used. But for this module you understand that this is another angle of the vacuum system. This is a chamber wall, alright, and these are the 4 source 1, 2, 3 and 4, right, in which you can load the material. Then there is a within the, this is a camera installed within the chamber, that is why you can see it. And you have, instead of in case of thermal evaporation it is by heat, but there is a difficulty with thermal evaporation. And what can be the difficulty? The difficulty is that if your source melting point of the source material or source substrate or source metal, which can be tungsten, right, if it is equal to or less than your deposition material melting point, what will happen? That the source will melt early before your deposition material, right. This should not happen, because if you see the holder, this particular holder, this should not get melt. We want the source material to get melt, which is this material which is loaded inside the source and not the source itself, alright. So, when you have the deposition material temperature extremely high compared to source material, in this case thermal evaporation cannot be used, and for that we have a system called e-beam evaporation that we will talk in a next module. But let us finish this one by talking about one more slide, which is the thermal evaporation of alloy. Now, if you want to have thermal evaporation of alloy, then you already know that binding energy of metals in alloy is different than that of binding energy of atoms in metal, and generally metal atoms are less tightly bond than atoms in an inorganic compound. So, if you take an example, so that what happens is one will evaporate faster than the second one, right. So, if you take an example, A and B are two materials and AB is an alloy, then activation energy of AB bond is different from activation energy of AA and BB bonds, and that means that metallic melts can be considered a solution of two materials. Partial pressure of A in AB at temperature T, let us consider as PA, cannot be equal to partial pressure of pure A at TPA 0. Similarly, case for B. So, we can have equation as PA equals to, we can write gamma into XA PA or rho A 0, where gamma A is your activity coefficient and XA is the mole fraction of A. Similarly, we can have PB which can be equal to gamma B XB PB 0, where gamma B is the activity coefficient and XB is the mole fraction. So, the flux ratio can be given by this equation which is shown here. Of course, this is a part of the equation under root MB by MA, where MB and MA are the atomic weight of B and A respectively, and that means that the vapor pressure as a film composition depends on temperature and the properties of material. In some cases it is difficult to deposit alloy. There are techniques called two source evaporation techniques. two source evaporation technique where both the sources are heated at different temperature, so that to evaporate the metal simultaneously and form the alloy. However, like I said, there will be cases where your deposition temperature, the material that you want to deposit, its temperature is extremely high compared to your source material. For example, if you want to deposit silicon dioxide melting point is very high compared to tungsten. So, it is very difficult to deposit silicon dioxide in thermal evaporation. Same thing goes for silicon nitride, very difficult to deposit in thermal evaporation, and that is why there is another technique called electron beam evaporation, which we will see in the next module, and we will go in detail about how the e-beam evaporation works and how it can overcome the limitation posed by thermal evaporation, where the melting point issue would not be there. So, till then you just look at this module. It is a very small module to help you out and not to confuse you with different PVD techniques. We will just look at PVD, we will not go into depth of CVD. Again, the reason of teaching you PVD techniques is that we use PVD technique for depositing metal, and those metal can be patterned using lithography to form your electrodes, which we can use for measuring the body vitals, either is ECG or EMG or EEG. Alright. So, till then you take care. I will see you in next module.